Okay, this video covers several different topics all in one video. So the first unit was on rational expressions, those that are in a fraction. The second unit was on conics and the different sections in the graphing and writing equations. And the last unit is our first unit on trigonometry, basically intro to trig and unit circle. So let's kind of go through some snapshots of the key topics in each unit. Okay, so rational expressions. The key to combining rational expressions whenever we're adding terms. Okay, so here's the term, here's the term, and here's the term. We have to get a common denominator. So I'm going to find out the factors of each denominator. Here, this is a 4 and an x. This is really an x times an x. And I'm going to factor the last one, take a 4 out, and then we have x minus 1. So notice if I have a common denominator, it's going to be, I need a 4, I need an x squared, okay, those two x's put together, and then an x minus 1. So over here, I'm going to add what's missing. So notice this one here, I'm missing the x minus 1. So I need to add it to the top. Here, I'm missing simply, I have the x squared, but I'm missing the 4 and the x minus 1. And then this last one here, the only thing I'm missing is the x squared. So now I'm going to go through and rewrite the top, and I'm going to factor the top here. So better yet, let me first maybe write it out. So we have 4 times x minus 1. And then we have 3x, then times the 4, then times an x minus 1. And then the last one is a minus 5x squared. So what I want to do now is distribute. So I'm going to rewrite the top down here. So I have 4x minus 4 plus, and then here we have 12x squared minus 12x, and then minus 5x squared. Okay, and all I'm going to do now is combine like terms. So the x squareds go together, and we have 7x squared. And then we have the x's next, which are here and here, so minus 8x. And I only have one number here by itself, so there. So that's the numerator, and the denominator again is a 4 times an x times the x minus 1. Okay, and again, what you want to do is you want to look to see, can I break this down and factor this out? This one does not break down, but this is what we're shooting for in this example right here. Okay, so let me go ahead and just minimize this now that we have that on here, and make it a little smaller so we got some room here. So let's put that up there. Okay. All right, let's take a look at this example here now. Now here's the same thing. So we have the bottom here. So I need to get a common denominator. So here I need to add an x. So I'm looking at common denominator for the top. So we have basically 2 minus 4x all over x. And then the bottom I'll do in a different color here. So let's put that there and then put the bottom back in red. So put this 3 over 1. So I'm going to add an x to both of them. So we basically have 2 plus 3x all over x. Okay. Now what happens when we divide by a fraction, we have to take this fraction, put it upstairs, and flip it. Okay. So I'll make a little note here. So now I'm going to rewrite the problem. So we have 2 minus 4x over x times, and then I'm going to flip the bottom part. So let's show it over here. So we have an x on top, and then the 2 plus 3x in the bottom. And notice in this case, the x's cancel, and we're left with simply 2 minus 4x over 2 plus 3x. And again, we can't really factor that anymore, so that would be considered our final answer. So we have to get a common denominator to both top and bottom, and when you divide by a fraction, it's the same thing as multiplying by the reciprocal. All right, let's take a look at our example here. Solving is very similar. If we want the two expressions on each side of the equal sign to equal each other, that means we have to have a common denominator and a common or equal numerators. So here I'm going to find a common denominator, which is going to be x and then x minus 5. Those are the two factors that I need. So notice this one, I'm going to need both. Okay, kind of ran a room there. This one, I'm going to need the x. And this one here, I'm going to need the x minus 5. Okay. And when we do that, the common denominators are all the same, so we can basically ignore the bottoms. So let's rewrite it over here. So basically we have 1 times the common denominator, which is x times x minus 5. And then we have minus 8x. Okay, just distributed that. Equals, and then let's go ahead and distribute the other side. So 3x minus 15. Okay, I'm going to go ahead and distribute that as well. So that should be x squared minus 5x minus 8x. And this side hasn't changed. Notice I can do this now because the denominators are now gone, and I'm able to put the two numerators equal to each other because the denominators were now the same. So now I'm just going to combine what we have here. We have an x squared, so it's quadratic. I'm going to move the 3x over, so we have negative 12x minus, I'm sorry, minus 13x, so minus 16x altogether, and then move the 15 equals 0. I'm going to factor that because it's a quadratic, and that's going to be x minus 1, and then x minus 15, and zero product law says that x will equal either 1 or 15. So we can see that right there. Okay. So what you have to check though is you have to make sure that those solutions are not a part of the domain restriction. So what numbers cannot we not have in the denominator? That would be 0 and 5. So those are the two domain restrictions. So 1 and 15 are not those two numbers, so those are both valid answers right there. So those look good. Okay. Now multiplying rational expressions, we want to again factor. So I'm going to take this first term and I'm going to factor it over here. So I'll do it in a different color. Do this part in red. So we're going to take out a 4, and then we have x minus 1. And then the bottom is going to be x minus 2 and x minus 4. And then what we're going to do is multiply, and I'll do the second fraction in black here. And because of the division, I'm going to flip it and make it multiplication. So I'm going to factor the bottom, but I'm going to put it on top. And notice I take the top, and what's that going to be? X minus 2 and x minus 1. Now we're going to look through and say, okay, what can I cancel here? Okay, so let's see here. X minus 2, top and bottom are gone. And then we have x minus 1, x minus 1. And that's really about it, because notice the signs here are different. So I'm going to take what's left over and only highlight what I got left. I got a 4, I got this, and a this. So let me rewrite that as a complete answer. The numerator is 4 times x plus 2. And then the denominator, we have x minus 4, and then we have x minus 2. Okay, so those are the different things there. So notice we're able to reduce factors. Okay, we cannot reduce terms, only parentheses that are factored out. Okay, so now with graphing, so we have several different things here to look at. So here we have a rational expression, numerator and denominator. And we have these different things to come up with. What's the domain, which define vertical asymptotes? What's the end behavior, horizontal asymptotes? And then some couple key points or gates, as we call them in here. Again, I use the Buffalo notation here. And a couple key points is we always have to run along the fence. The Buffalo run in opposite directions when on opposite sides of the fence. And if you have designated points or gates, then you have to go through those. So let's kind of go through and talk about each one. So the first one says, okay, the domain is when the bottom is equal to 0. So this is really x minus 3 and then x plus 3. And it's setting it equal to 0, so the two values of that are going to be at positive 3 and negative 3. So I'm going to throw my asymptotes in at x equals 3 and x equals negative 3. So let's draw those in. Again, they're just guidelines, so here's my fences. So this is going to be x cannot equal positive or negative 3, but it does include all real numbers. Okay. So the asymptotes themselves are those equations, x equals 3 and then x equals negative 3. So that's the difference between that. Now horizontal asymptotes, that's end behavior. So this is the game. If the bottom is bigger, notice here, x squared is bigger than x. Don't look at the coefficients, then it goes to 0, and it looks like that. If it's a tie, looking at the degrees, x squared and x squared, then you look at the coefficients, 3 over 1, so then the horizontal as it approaches infinity to the right and left, it will approach 3. Then if the top wins, for instance, x squared is bigger than x by degree, then it doesn't have a horizontal slope and it just carries off into space, both in opposite directions in this case here. So let's look what we have here. So here we have x to the first power on top and x to the second bottom. So then the bottom wins. So I'm going to say the bottom wins. Therefore, approach y equals 0. Okay. So we're going to draw another asymptote in here at y equals 0. Okay, so now we got kind of some restrictions. Let's go ahead and figure out some intercepts. So let's go to do this one in black. The x-intercepts are when you're basically solving it. So I'm going to set the top equal to 0. So notice we're going to have -4 is equal to 2x, and basically -2 is equal to x. So let's put a dot at -2. And then another good point, so if I write it as a point, it's going to be -2 comma 0. And then to get the y-intercept, we plug 0 in for x, and use this evaluate. So if you do that, you basically eliminate the x's, and you have -4 divided by -9, which is positive 4/9. So we do this to get two very simple points, okay? And looking at our 2 points, we can see how would the buffalo run? Well, he's going to connect these 2 dots, go against the fence, and then bend along the fence and go north. Here, he's going to go in this direction and bend this way, okay? Now, in doing that, if it goes up here, then it has to go down here in opposite directions and fill this quadrant, okay? And then same here, if it goes down, then I need to start in the up position, come down, bend along the fence, okay? So there's a very quick way to sketch graph based on the asymptotes and restrictions, and then the general direction of the curves, okay? Again, you could always evaluate, +10 or -10 into the function and say, am I on the positive or negative side? So that's another thing you could look at here as well. Okay, so let's now look at conics. So again, the different conics we looked at was parabola, circle and ellipse, and hyperbola. And seeing the graph here is the different angles of section. So a parabola is parallel to the angle of the cone. A circle is perpendicular to the axis, whereas ellipse, it's tilted a little bit, so it's a circle that's stretched in one direction. And a hyperbola is when it goes basically straight up and down, or at an angle greater than the angle of the cone. So how do we look at it in equation form? Well, parabola, only one of the terms is squared, and the other one is to the first power. A circle and ellipse is where you have the x squared plus y squared, so they're both being added to each other, okay? A circle is where the coefficients are the same, so we have as our r squared. Ellipse is where the coefficients are different, and that's why we have the fractions down here. A hyperbola is a lot like the ellipse, but the only thing different is it's a subtraction. So we have x squared minus y squared, or vice versa. And that determines if it's a horizontal or vertical ellipse. So let's go ahead and take a look at some examples of these shapes. All right, so here we have in standard or graphing form the equations. So notice we have the squared term, which is x here. Then the 4p, that tells us our focal distance and focal width and that nature. And then we have y minus k. Notice we have two different versions. Is the x being squared or the y being squared? That tells us it's going up and down if the x is squared, or left and right if the y is squared. And then the positive or negative value of the p tells us the direction left or right or up or down. So here's an example. So let's go ahead and find a vertex. So I'm going to look at the hk. So I take the opposite of +3. So we have -3, 2. So let's go ahead and graph that. -3, 2. And then we have the axis of symmetry. So we got to determine, what do we have? We have the y is being squared and not the x. So that means it's going sideways. It's a -8, so it's going to go into the left, okay? So if I was to sketch a little curve, it's going to look like that. So the axis of symmetry then goes down the middle of the vertex, like such. So we'd say the axis of symmetry is y is equal to 2, okay? Then the focus, okay, we have to find the focal distance. What's the p? Well, 4p is equal to 8, therefore p has to equal 2. So from this position, I am going to move 2 dots in for the focus, and then 2 dots away for the directrix. And again, the directrix, I'll do it here in red, is the line that's on the outside of the curve. And this line here would be defined as x equals -1. Now I'm just really looking at the graph. So the focus is what the curve goes around. So the focal width, okay, the width is equal to 4p, and that's the focal width. So from here, that would be 8. So I'm going to go up 4, and then we'll go down 4. And that gives us a couple guidelines, so I'll trace this here in black. And we could see the curvature of the parabola looks like this, okay? And notice we're able to define the focal distance, the direction of the curve, the equations of both the directrix and axis of symmetry in this situation, okay? All right, let's look at the next shape. I put circle and ellipse together because they have similar properties, but of course they're different. So I'm going to put them both on the same graph here. So let's take a look here. Circles are simple. We have the starting point and radius squared. So let's go ahead and look at the example. The center of the circle would be 2, 6. And again, we'd take the opposite when it's in the inside of parentheses like such. So we have 2, 6. And then what's the radius? That's going to be the square root of 9, which in our case is 3. So we have, I'm just going to couple guide points here. 3 units away. I'm going to sketch in a circle. My circle skills are not really good today, but it looks pretty decent. Okay. All right, so let's go ahead and take a look at ellipse. So here we have the same starting point where we look at the inside of parentheses. So in this case, it's going to be -4, -5. Okay, so we take the opposite signs. And then what we do is for our A and B. So A is the major, the bigger one. So the square root of 25 is 5. And then this one is the square root of 9 is 3. Now to get the C factor, we look at this equation up here. Okay, and we take the big minus the small. So 25 minus 9 is going to be 16. And the square root of 16 is 4. So right there we can get our dimensions. And the C is for the foci. Okay. So let's go ahead and kind of sketch this. So we're going to have a starting point at -4, -5. So -4, -5. And since the 25 is associated with the x, and then the major axis is the bigger one. So I'm going to go to the right 5. That's 1. And then 5 this way. And then 3 up and down. So that gives us the actual outside curvature of the ellipse. So I'll sketch that in here. Now the foci are C units away from the middle. So I'll put those in a black dot here. So we go over 4 here and 4 here, and there's the foci. Okay. So obviously you can pick the coordinate points from here as well. But what's the major axis length? Well, that's 5 this way and this way, so that's going to be a total of 10. And then the minor is 3 up and 3 down for a total of 6. Okay. So just going through the principles of how to pull out the right information from the equation and be able to associate with the graph. All right, let's take a look at the last example here of a hyperbola. Now notice the one thing that is different is the minus sign, so that is key. So actually I have a little typo here, so let's fix that. That should be a minus sign, sorry about that. So let's make that correction right there. And so let's go ahead and determine the center. We do it the same way. We look at the points here. So we have 4, -2. And then our A value, now again, this is the positive value, and the B is the negative coefficient. So we have a positive square root of 4, which is 2, and then the negative is the square root of 9, which is 3. So a hyperbola is different. It has a positive term and a negative term. And then the C value is basically adding these two values together. So what's 4 plus 9? Well, that's going to be 13. Okay. And since we're taking a square root of that, it's going to be the square root of 13. So let's go ahead and start plotting this. We have a center at 4, -2. So over 4 and then down 2. And then from here, we're going to go right and left 2. And then back 2. And then we're going to go up, down 3. So I know because the x goes with the 4 and the y goes the 9. So y's go up and down. So that's where we get our up, down, and left, right directions. X and Y. And then what I'm going to do is, I'm going to draw these. These are supposed to be dashed lines, but I'm going to draw them solid just so we can see a better picture. But I'll do all the asymptotes and restrictions in red and the actual graph in black. That was kind of not the best. Let me undo that box here real quick. This won't let me. So either way, and now we're going to draw my asymptotes in, and you draw those through the diagonals of the box. So let's go ahead and find the equation of those asymptotes. These are really bad lines here right away, guys. All right, so the equation, I'm going to use point slope form, which we see right over here. Okay, so it's going to, again, be y minus, and the point I'm going to pick is the center. And we can see it right here. So it's going to be y minus negative 2, so it's y plus 2, equals the slope, and then x, minus 4. Okay, so it's the center again. The center of 4 comma negative 2. So it's the exact same parentheses as above. But then the slope. So what's the slope? Rise up 3 over 2. And I like to look at the graph. So don't think it's A and B. It's associated with those numbers, but you have to look at the orientation. So in this case, it's up 3 and over 2. And since there's two lines, the only difference is a positive and negative slope. So I can write both equations looking like that. Positive and negative slope there. Let me kind of rewrite that so it doesn't look like a positive on the top. And so we really want positive and negative up front, and then 3/2 to signal that it's two different equations there. Okay. All right, so based on this, let's go ahead and draw in our curve. So it's going to start at the vertice and go this way, hug along the asymptotes, and the same on this side here. And again, I'm just sketching this. This is actually pretty horrible of a drawing for me. So we can see the difference there. So let's go ahead and figure out the points now that we have all the orientation on here. So the vertices we'll see right here. So it's going to be 6 comma negative 2. And then the other point is obviously 2 comma negative 2. And then for the co-vertices, those are up and down. So that's going to be 4 comma 1. And I'm literally just pulling it off the graph. And the other one is 4 comma negative 5. I'm sorry, hold on. 4 comma, yeah, negative 5. Looks better. Now the foci are the dots that are the square root of 13. So that's a little more than 3, not quite 4. So it's going to be a dot there and a dot there. Okay, so how do we write that? Well, we start with the center, which is 4, and then we add and subtract the c distance, which is the square root of 13. Then comma, and we're only negative 2 down. So that is the best way to, I'm going to rewrite that last number. That's the best way to show the foci because it's accurate. So it's 4 plus or minus square root of 13 comma negative 2. Okay, so that covers hyperbolas. Now let's go ahead and take a look at how do we take something from general form, which notice it's in order, the highest degree in front, and then equals, and then 0. So everything's on one side of the equation. And we want to convert it to graphing or standard form, which is completing a square. So the first thing I want to do is organize my x's. So I have a 16x squared minus 32x. And then I'm going to organize my y's. And I'm going to go ahead and throw the number on the other side of the equation. Next, I'm going to factor out the leading coefficient here, so I can complete the square. And I'll do the same for the y's. Leave my blanks for the last number. And then I'm going to add 2 blanks to the end here. Okay. Now notice this, what I'm looking at is a ellipse because they're both positive terms. Now if this was a negative, that would change and it would become a hyperbola and we'd have to subtract this last number. But we should know that difference there. So now complete the square. So this is a 16. This is x minus 1 quantity squared, so that's a 1, plus 4, and then I'm going to take the 4, cut that in half, square it, and put a 4 back here. Okay. Now again, what am I adding here is we're adding 16 times 1, so 16 goes there, and then a 4 times a 4 for another 16. So now if I add those all together, I'm going to get 64. Now, since it's an ellipse, we want to divide everything by 64. We want to force that last number to go to 1. So now we're going to have x minus 1 quantity squared all over 4, because that reduces. And then that reduces to y plus 2 quantity squared all over 16. So there's my a and b value. So actually a is here because it's the bigger one, because it's an ellipse, equals 1. So that here is standard / graphing form whereas this up here is general form. They're both the same equation, and they produce the same graph, but they're just different forms for different purposes. All right, so let's talk a little bit about trigonometry, and this should be very familiar with us. So we have a theta, which is the point of reference of your triangle. We have opposite, adjacent, hypotenuse, and we have the 6 trig functions. So I'm not going to read through them all, but we should know them as opposite over adjacent. Um, I'm sorry, opposite over hypotenuse, adjacent over hypotenuse, and then opposite over adjacent, and then the reciprocal functions over here. But I'm going to go through a ordered pair point to show us the same thing. So let's go ahead and graph -3, comma 4. So notice we went back 3, and then we went up 4, and then if we use Pythagorean's theorem, we realize that's a 5. So we're going to find that ordered pair right there. Okay. So if we go through the trig functions here, what is, and the theta is, really that rotation there. That's theta. But then it's the same as the reference angle on the inside as well. So let's go ahead and take a look here at what's going on. So sine is opposite over hypotenuse, so that's going to be 4/5. And then cosine is adjacent over hypotenuse. So again, we carried a sign, so it's -3 over 5. So that tells you what quadrant we're in by doing that. Tangent is opposite over adjacent, so it's going to be 4 over -3. Now for the reciprocal functions over here, all we have to do is flip the fraction. Okay. Now obviously if these were radicals, you would have to rationalize and alike, but we don't have that case here, so we just leave it like that. Okay, so those are the 6 different functions that we need to know, and I want to show a coordinate point problem so we can see how the negatives and positives work in that regard too. All right, so let's take a look here at the difference in rotation. So we have degrees. So the thing is, we always start at 0 here, and in positive rotation, we rotate counterclockwise. So that's positive. Now if we go negative direction, then it goes clockwise, okay? And it's the same for radians over here. Now, one rotation for degrees is 360 degrees. One rotation for radians is 2 pi, and that is equivalent to the circumference based on the radius, okay? So those are the different keys there. So let's go through, for instance, an example of terminal and coterminal and initial side and things of that nature. So let me erase this out of the way first. So let's say we had let's keep it simple, a 30-degree angle. Okay, so there's a couple ways you could list this. We could list it as a positive. Well, let's talk about this. This is 0, so we call that the initial side. So let's go ahead and label that. So we call that the initial side. And then the terminal side is where you end up. So that's where the line is right there. Okay. So there's a couple different ways to list this. In a positive rotation, we'd say positive 30. But if we went backwards, we would rotate negative 330. Okay. Now let's say we went ahead and said we want to go around a circle one time and then add a little bit more. So you would have rotated 360 plus 30 more, which would be a difference of 390. Okay. So notice all 3 of these angles have the same terminal position. Okay, it's this number of rotations. So we call these coterminal. Okay, and that's very important to realize. Okay, because that's going to be important when we do inverse trig and isolating what answer is associated with the right problem. Okay, with radians, it's the same thing as well. But the only difference here is we still have the coterminal rotations of different types. But if this is 0, your initial side, and this is pi, and then you rotate one more, and you're back at 2 pi. Okay. So the nice thing is, so let's pick the exact same terminal piece. So a 30-degree angle in radians is pi over 6. I'll show how to convert that here in a second. So how do we get coterminal elements here? Well, it's very simple. If we have pi over 6, we just add another 2 pi to it, and you would say, 2 and 1/6 pi if you want to do that. Okay, we don't only show us mixed numbers, so we would convert that to 12 pi over 6. That'd be the best way to do it. And then 12 pi plus another pi would be 13 pi over 6. So you're basically just adding or subtracting 2 pi. Whereas in degrees, you're adding or subtracting 360 degrees, okay? Now the last thing I want to show you here is how do we go from one to the other, okay? So I'm trying to delete that there. So let's take our 30 degrees and transfer it over to pi over 6. So if we start with 30 degrees and we want to end up in radians, which is pi, how do we get there? Well, you got to do a unit conversion. If degrees are on the top, then you put degrees in the bottom and put pi, what you want to keep, on the top, and that should go there, okay? So now we have what's 30 divided by 180, and that's 6. So we have 1/6 pi. Okay. Now, if we want to go in opposite direction, let's start with pi over 6, and you want to end up with something with degrees. Then we want to get rid of pi, so I put pi in the bottom and put 180 degrees on top. This way, the pi's cancel, and what's 180 divided by 6? Well, that would simply be 30 degrees. So we have to know how to convert from one to the other. Okay, and that can go for any degrees. 30 degrees is a pretty simple one to do, but you can use that conversion for any radian or any degree. All right, so unit circle was a big part of this. Again, you're responsible for all this information. And what we have to do is we have to realize that they're all associated with these values here. 1/2 root 2 over 2 and radical 3 over 2. And I call them small, medium, large. And they're based off of a 30, 60, 90 triangle and a 45, 45, 90 triangle. And again, we use Pythagorean theorem to derive those numbers there. But the key for me for a unit circle is you have to understand the reference angle, the quadrant, and the sine. So I didn't talk too much in the last slide about reference angles, so let's kind of do it here. So let's just pick 210 degrees. So that means I'm going to start here and rotate 210 degrees. So reference angle is how far are you away from the horizontal line. So that means I have a 30-degree rotation from the left horizontal line. So my reference angle is 30 degrees. So I have a 30-degree reference angle, and the second question is what quadrant? In the third quadrant. Now, being that it's a sine, sines are positive in the bottom quadrant, so we're going to have a negative 30 degree, or a negative sine, 30-degree reference angle in the third quadrant. So what is the rotation here? Well, that's a small for us, so it's 1/2. And again, I'm looking at my values up here because we have a shorter displacement vertically away from the middle, and that's our value, okay? So let's go ahead and look at tan of 4/3 pi. So that would be 4/3 pi is right here. Now for tan, we wanted this order pair right here. So we have basically sine over cosine. So let's get our two values. The sine value of this is negative square root of 3 over 2. And then the cosine value is negative 1/2. Okay. Now notice if we look at it, they both have a divide by 2 on it, so we can ignore that because those cancel out. And basically, the two negatives cancel each other out and become positive as well. So what is the tan of 4 pi over 3? It's just simply the square root of 3 divided by 1, which is simply this, the square root of 3. Okay. Now, the last thing we're going to look at is what's the secant of 150 degrees. Let me go ahead and kind of erase that so we get some room. And 150 degrees is right here. So again, the rotation is to here, but what's my reference angle? We have a 30-degree reference angle in the second quadrant. And being that secant is the same thing as 1 over cosine, cosine is negative in the second quadrant, so we know our answer is going to be negative. And what is the cosine value here? We have square root of 3 over 2, but I need to flip it because it's secant, which is the reciprocal. So it's 2 divided by the square root of 3. And the last, we need to rationalize that. So in the end, negative 2 square root of 3 all over 3 is going to be our final answer. So that's an answer there, that's an answer there, and that's an answer there. So again, you need to evaluate the unit circle and be very familiar with that. We talked about numerous different ways to do it, but in the end, that's what we're looking at. Okay, the last thing we're going to look at associated with the unit circle, and not just unit circle, is inverse functions. And we have basically 3 different default situations, okay? We have a default answer, which gives you one answer like the calculator would. But if I say, okay, give me all possible answers from 0 to 360, you could really have up to 2 answers. And in general form, how do we show all possible answers? Like every coterminal degree that goes with it. So up here we can see a graph showing the different default range. So sine and tangent is that half moon from negative 90 to 90, whereas cosine is the setting sun from 0 to 180. Whereas 360, notice it's a bigger domain, okay? So let's do sine of theta is equal to 1/2. So again, to isolate that, we'd have to do an inverse function. So I do sine inverse of 1/2 equals theta. So now that theta is by itself, and I did it by doing an inverse function where you switch the input and output. So now theta is by itself, so I could plug this into a calculator or use my unit circle knowledge and say, where do I have sine is equal to 1/2? So let's just kind of sketch a unit circle. Sine of 1/2, I have it in the first quadrant with a 30-degree reference angle. And I also have it in the second quadrant at 150 with a 30-degree reference angle. So 30 and 150. So up here, I would see it here and here. So I would have two answers from 0 to 360. I would have a 30-degree angle and 150-degree angle. Okay. Now, which one's the default answer? Well, this one is the only one that's in the correct range or the correct domain. So 30 is your single default answer. Okay. Now, for all possible answers, what I'm going to do is take the 2 points that I found in a single rotation, and then I'm going to say, okay, what if I take 30 and add 360 to it? Okay, so that'd be 390. We saw that before. So how do I express that? You add 360 plus the number of rotations, n. And n is defined as an integer, both positive and negative. So we just simply express it in that nature right there. Okay. So that's kind of a little overview of inverse functions. Okay, next we have law of sines and cosines. Okay, and the key to this is you have a triangle that's not a right triangle. And how do we find, all the missing pieces? So the key is you have to have a matching pair. We talked about Dr. Evil and Mini-Me. We have to have a capital A and a little a, and you have to have both pieces because we want to use law of sines. That's ideal. Now, if we don't have a matching pair, then we use law of cosines to find the missing link. Once we have the link, then we can go ahead and set up all of our ratios for law of sines and find answers. So let's go ahead and look at an example here of a problem. So let's go ahead and sketch our triangle. Let's label it A, B, and C. And let's fill in information. We have a 90-degree angle at B. A is 34, and C is 28. Okay, so based on that, I want to find a matching pair right here. So I need to find little b. So I'm going to use law of cosines right here. So b squared is equal to a squared, which is 34 squared, plus c squared, 28 squared, minus 2 times the value of a times the value of c times cosine of a, in this case, or I'm sorry, cosine of b, which is 92. So notice the only thing we have to solve is the b value, okay? So in this case here, use your calculator, take the square root, and we find out that b is going to be 44.79. Okay, I just rounded it, but on my calculator, I'm going to store that value. I don't want to round in the middle of the problem. So now that I have that, I can set up a law of sines. So we have sine of b, which is 92, divided by 44.79, and keep all those decimals, is equivalent to the sine of a, which we don't know, over 34, which is equivalent to the sine of c divided by 28. Okay. And again, in this case here, you would use your calculator. You set up like a cross multiplication. So if we were to do a, we would just look at those two pieces there. We would cross multiply and divide out. So in my calculator, I'm going to get sine of a is equal to 0.759. So again, here we have to use the inverse function of 0.759. And I keep all those decimals stored in my calculator. And then what does a equal? Well, a turns out to be 49.3. So I'll just write it up here, 49.3 degrees. And if we did the cross multiplication for angle C, it ends up being 38.7. Okay. And notice if I add all those up, they're going to equal 180 degrees as well. Okay. So there's an overview of how do we use law of sines and cosines to solve triangles that perhaps do not have a right angle.